The 5.1 notes the storyline for this centers around zombies. And so here is the setting up the story here. We have on the show The Walking Dead, a disease contracted that turns people into zombies, or in other words, walkers. If a walker bites a human, the human is turned into a walker. Assume each walker in turn bites one person a week, and that person was transformed into a zombie, and that none of the walkers are killed. Okay, so what we want to do is we want to take this scenario and first of all look at it numerically, but then eventually model it into a mathematical formula. So the diagram below represents the town with 140 people, and it says each box represents a human. So there's 140 boxes down here. And it says each crossed out box represents a walker. So it's a person that's already been turned into a zombie. So what we start out looking at the diagram and looking at the table, what we start out with is that in this population of 140, we have one zombie. And we know that every week a walker turns one person into a zombie. So when we start out, we just have that single zombie in the population of 140. And then that week, that zombie bites another person. And now we have two zombies. So after that first week, we now have two walkers or two zombies. And so now we got two of those creatures roaming around. And that next week, they both bite somebody. So if they both bite somebody, now we have 4 zombies in this village. And then the following after that, these 4 zombies each bite a person. And if they each bite a person, that means we've got 4 more zombies in the population, so we have a total of 8. And we continue. The following week, these 8 zombies bite somebody, and we got now 16. And the week after that, those 16 zombies all bite a person, and we now have 32. And the week after that, oops, there we go, 32. The week after that, all 32 of these zombies bite somebody, and we now have 64 zombies. And we're going to keep going, right? Because we still have a good part of the population that aren't zombies. So these 64 zombies all bite somebody. And we now, as you can see, we're now growing zombies at an alarming rate, right? So we now have 128 zombies. And so just to get back on the population grid here, let's just move these zombies back into the population grid here. And so we've got these 128 zombies, and they're going to continue biting. So the idea is if we had an unlimited population, these 128 zombies could continue to bite, and we would have 256. But we have at this point, because we're in this small town, and there's nobody coming in and out of this town, you know, like these really bad movies, we're up against a population limitation. So at this point, you know, we got 128 zombies. They could potentially bite 128 more people, but since we only have 140, then at week 8, the remaining people who haven't been bitten yet, which looks to be about 12 people, right? Those 12 people get bitten, and now the whole town are zombies. Like I said, if we had an unlimited population, we could keep doubling the week before. And so that's really what we're going to focus on, is we are going to focus on this pattern of doubling. So we're going to focus on this pattern of doubling and model that with a mathematical equation. Okay, so just to answer these questions down below, how does the walker population change each week? It doubles until we run out of people. And it says, how long will it take for everyone in the town is a walker? And that happens right there between 7 and 8 weeks. And it says, list the number of walkers as a sequence for the first 7 weeks. So what we're looking at is, let me change the color on this highlight. Let's go with pink. So what we're looking at is taking those numbers for the first 7 weeks, and we're literally listing them. So this list that they're asking us to make is called a sequence. It's a list that follows a pattern. So we started out with 1, and then we had 2 and 4, 8, 16, 32, 64, 128. And so because this sequence is a doubling sequence, or in other words, we get the next number in the sequence by multiplying by 2, and that's the pattern. So we are multiplying by 2 just to get that next number as we go through the sequence. We call this a geometric sequence. And geometric sequences are sequences that are made by multiplication or division. So that's called a geometric sequence. And what we want to do is we want to be able to model this with a mathematical representation. And we can do that a couple different ways. The first way we're going to model it is recursively. Recursively means to write an equation so that we can find the next number in the sequence if we know the number before. So for instance, looking at the sequence, we start out at the beginning with 1 person. So that term is called the a sub 0 term, and we start out with 1 person. And then the next, after the first week, that doubled to 2 people. And after the second week, that doubled to 4 people. And so if we notice, if we want the third week, we're going to take the second week and multiply it times 2. Right, 4 times 2 is 8. So the recursive formula is like that. It has you find a term in the sequence, knowing the term before. So the way we write that in general is we want to find any generic term in the sequence, a sub n. We need the term before, which is 1 smaller than a sub n, and then we multiply it by that doubling pattern. So multiply it by 2. So there's a recursive formula, and that comes in handy to build the sequence term by term. So let's graph this sequence on this grid. So if we notice we have a grid here, we're going to graph that doubling pattern. We start out, and I'm really zooming in here because we have to start out at 1 person, and then we have to double it to 2, right? And so all of this thing is happening in this first row of boxes, and then we double it to 4. And then we double it to 8, and then we're finally doubling it to 16 out here at week 4. We're finally getting up above that first row of boxes, basically, on the grid. So I'm going to start zooming out here. And so if you notice, as what happens when we double, is those vertical gaps get bigger and bigger. So the next week, we're going to double it to 32. So we notice that gap growing. The week after that to 64. So that gap is getting really, really significant now. And the week after that to 128, which is way up here. If you notice then, with that graph, it's definitely not linear. We know this because the gap is getting bigger, that vertical gap, each week. So we that relationship starts to curve then as that gap changes. And then, you know, because of the population limitation, right, we top out at 140 after the 7th week in this isolated little town. We just stay at 140 and the whole town are zombies. And again, we're not really concerned about modeling that because nothing's changing. We're just concerned about modeling as we have that doubling pattern change. As we are having that doubling pattern progress, I guess you could say. Okay, so let's switch gears a little bit and go through the same sort of idea. And now, instead of starting with 1 zombie, we're starting with 3 zombies. So we're just going to see how changing the start value affects that sequence, that pattern. And so we start with 3 zombies. And everything else is going to hold true. We're going to take the 3 zombies. They're going to bite 3 people. And after the end of the first week, we now have 6 zombies. And then each one of those zombies are going to bite somebody. And we now have 12 zombies. And so we're going to continue this doubling pattern. And so these 12 zombies bite people. And we now have 24 zombies. And the 24 zombies all bite a person. And we now have 48 zombies. And then the 48 zombies all bite somebody. And we now have 96 zombies. And let me move these zombies back into the village here. So I'm just going to grab 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm going to grab these 8 zombies, get them back into the village. Grab these 4 zombies, get them back into the village. Right, and if, again, at this point, if our village had an unlimited population, oh no, wait a minute, yeah, if our village had an unlimited population, we could then have those 96 zombies bite 96 more people and have 192 zombies, but our population is capped at 140. So those 96 zombies, some of them are going to bite enough people to then bite everybody in the population. So at week 6, that's when the entire population becomes the zombies again. And so now we're talking about 5 to 6 weeks. So it's happening faster, and it's happening faster because we started with more zombies to begin with. So let's make this sequence now. So this sequence starts at 3, and then goes to 6, then goes to 12, then goes to 24, then 48, then 96. And so we still have that doubling. We're still looking at this doubling pattern, right? This is still doubling. So the pattern is the same. It still doubles, so it's still times 2. And we can still get the next term by repeating that doubling. So it's still a geometric series. But because we started with a different number, we get different numbers in the pattern. And so this recursive formula now is, we're looking at we started with 3 zombies. So at the beginning, we had 3 zombies. But we're still doubling. So our expression, our recursive formula is still a to the n equals a to the n minus 1 times 2. Because that 2 is coming from the fact that we're still doubling our zombies each week. And so if we look back at the answer to 1C, that recursive formula really hasn't changed. This hasn't changed, but we just have a different start value because we're still doubling. So we can use this recursive formula and come up with, we can basically extend the sequence to answer these next couple of questions. And so I'm going to bring up my calculator here because we're getting into some pretty big numbers. But if we want week 8, well, we could take, let's see, right now we have week 5, right? We have A5 is 96, so I'm going to put 96 into my calculator. And then I'm going to go times 2 to get A6, and then times 2 to get A7, and times 2 to get A8. So, whoops, I divided by 2. Excuse me. Let's try that. Let's clear that out and do that again. So we start with 96 and times 2, that's A6, and times 2 again is A7, and times 2 again is A8, and we have 768 zombies if we have an unlimited population, right? We have an infinite number of humans. And we can keep that pattern going. So that's A8. So A9 would be multiplying by 2 again. A10 would be multiplying by 2 again. A11 would be multiplying by 2 again. A12 would be multiplying by 2 again. A13 would be multiplying by 2 again. And if you can see, the population is really growing. It's 24,576. And I can keep doing this. So that's 13. So let me quickly do this here. 14, 15, 16, 17, 18, 19, 20. So look at that, we're in the millions already. 21, 22, 23, 24. So we are looking at 50,000, excuse me, not 50,000, 50,331,648 zombies after 24 weeks. But, if you notice, I multiplied by 2. I had to do that a lot to get up to week 24. So the question is how can we figure out how many walkers for any week? So this gets us into a formula that's not recursive anymore. So what I have on my calculator right now is all recursive. And I don't want a recursive formula. I want to be able to find any number in the sequence, and I want to base it off that first number. And for us, that first number was 3. And so if we think about it, let's just kind of put that aside and kind of think about the pattern we're looking at, this doubling pattern. So we have a sub 0 equals 3, and a sub 1 equals 6. That's 3 times 2. And a sub 2 equals, let's see, 6 times 2 is 12. Well, that was 3 times 2. That's 6 times 2 again. And the third week would be then taking the second week. There's the second week and multiplying it by 2 again, right? And so when we look at this pattern, we can see that for the third week, I have 2 times 2 times 2. So I have 2 to the third power. So I could rewrite this as 3, my starting value, times 2 to the third power. And so that means if we can see that pattern here now between the week number, which is 3, and the power number, which is also 3, we can see that a general equation for us, or a general expression, would be to take 3, the number of zombies we started with, and we multiply it by times 2 to the n power. So let's try that. A24 then would be 3 times 2 to the 24th power. That should get us that 50 million mark. So let's try putting that into our calculator. 3 times 2 caret key and 24 power. And if you notice, it gets us that 50,331,648 zombies. So here's a formula. This formula is nice because we don't have to build the whole sequence. We can jump around and just get any number in the sequence without having to go through that task of doubling 24 times. So let's kind of extend that now, because this is actually a function. So if we look at this next statement here, it says for a certain area, the equation is this. And it gives the number of walkers y weeks after, give the number of walkers y after x weeks. Explain what the 6 and the 3 mean. So kind of connecting it to the previous statement, this 6 must be the number of walkers at the beginning. So this is the walkers at the start. So we started with 6 zombies. And this is representing the pattern that's emerging. So our doubling pattern was 2. So this must be a tripling pattern. So, so we're tripling the population of zombies each week. And so we can, if you notice, that's a little more like a function. If we wanted to write this as a series, we would go back to the notation of a sub n equals 6 times 3 to the n power. So we can write it as a series, or we can write it as a function. I'll rewrite the function. It's already in the problem, but I'll rewrite the function here. This is more like a function that you would graph. You know, it gives you that curve that we graphed a little earlier. So it's 2 ways of writing that relationship. So what we should come away from with then are kind of 3 learning targets. The first learning target is that we want to identify this as a geometric series. Okay, so geometric series are series where we have where we do successive multiplication, like we multiply by 2 each time. In the first one, we multiply by 3 each time in that most recent example. So that's a multiplying pattern. And the recursive expression looks like a to the n equals a to the n minus 1 times some rate, like if we're doubling or tripling. So that's we would call that a growth rate. So this is a growth rate. That's what that means. That's the, let me point towards the R there a little better. There we go. But we also can write it exponentially. And the exponential equation is the y. Well, let me write the equation that we just came up with, where we said it's the starting value a sub 0 times that rate. And we can write that as an equation as y equals, and then when we write it as an equation, we drop that a sub 0, we just call it a, and then the rate, we call it b to the x power. Oops, and I forgot the n over here, to the power n. So we can write that as an exponential equation, or we could write it in series form, or in sequence form, excuse me. And then the second learning target is the acknowledging that this is not linear. So we have to acknowledge that we have an exponential relationship here. So we have this general shape that looks like this on a graph, as opposed to having a linear relationship. So that this is the exponential, this grows by a common ratio. Right, it grows by multiplying, successive multiplying. Okay, and learning target number 3 is we're actually kind of circling back to learning target number 1, and that is the idea of writing it as a model or an equation. So we have the initial value a sub 0, and that is kind of transforming into just a. That's the initial value. And then we have a growth rate. So this was our doubling or our tripling. So we have this growth rate. And that growth rate is in the, let me slide that over. In the equation, that growth rate is expressed as b. So we have this equation that looks like a times b to the x. And then, so this is the initial, and this is the growth rate. Okay, so what you should do is do the check your understanding, and I've given you some answers along the way just to kind of give yourself an idea of whether or not you're on the right track. And then you can check your answers in Blackboard. We have full notes that you can check your answers against. And then the homework follows this, and here's the homework. And so the homework is really identifying, writing that equation. So if we just did the first one here as an example, we would have our first value, here's our a, and then we would look at our pattern. It looks like our pattern is times 3. So we would write this as, remember we're writing it as ab to the x power. So the x is the weeks, right? So we have this a is 1 times the multiplier, which is 3 to the x power. So that would be the equation. So you're looking at setting up equations for those tables.